Now we're going to consider irrotational flow. So irrotational flow is when the flow is not spinning. So if the vorticity is zero everywhere, the flow is said to be irrotational. So irrotational means no vorticity. This means that del cross U is equal to zero everywhere. So if del cross U is zero everywhere, that opens up a possibility for mathematically studying the flow that does not exist if the vorticity is non-zero. So let's take a look at what that is about. So imagine a function which we're going to call phi, and almost everybody calls it phi. And phi is a function of x, y, and z. And what phi is a function such that when you take the gradient of phi, you get the velocity vector. So the question is it possible to do this? It would be nice, but is it possible, mathematically speaking, to find a phi that represents the u vector like this? So that's the question. So, well, we can say we know what grad phi is. Grad phi is equal to d phi dx, d phi dy, and d phi dz. So that's just the definition of the gradient. So I have the three derivatives there representing grad phi. If I take the cross product of grad phi, I would find the vorticity, right? So vorticity, psi, is equal to del cross u, but grad phi is supposed to be equal to u. So del cross grad phi is supposed to equal u. So that's my thing, right? So let's see what that does. So I have del cross grad phi. I need to find that. So I'm going to put my three rows, my del row, d by dx, d by dy, d by dz, and then my grad phi row, d phi dx, d phi dy, and d phi dz. So those are my two rows to calculate my cross product. And so I'm going to do it. I'm going to get my first element is the x element of this. So I'll say that equals. My first element is, cover that up. I have a second derivative of phi with respect to y and z. So I have d squared phi dy dz. And then minus second derivative of phi with respect to z and y. Z dy. That's my first element. My second element, this is all in a big vector. I cover up the y. I have negative of this one. Second derivative of phi with respect to x and z. D squared phi dx dz. A big minus sign out front, sorry. And then minus second derivative of phi dz dx. And the final one, the z component, d squared phi dx dy minus d squared phi dy dx. So if you look at these, I have second derivative dy dz minus second derivative dz dy. Well, for smooth continuous functions, those two equal each other. So that's going to be 0. And I have second derivative dx dz, second derivative dz dx. Those also equal each other. So that's also 0. Second derivative dx dy minus second derivative dy dx, smooth continuous function, that's also 0. So the vorticity for that case is equal to 0. So it always has 0 vorticity if you have a function that is able to represent your velocity field by means of the gradient. So the conclusion is del phi can equal u only if psi, the vorticity, is 0 everywhere. So if vorticity does equal 0, we can use phi to represent velocity. This has some mathematically powerful implications for us. So we're going to be able to use that. If the flow, the final way to say this is if the flow is irrotational, we know that means irrotational, that means no vorticity, we can represent the flow field with a potential function. So that's what this phi thing is called. So that's a key word, potential function, and usually, almost always, it's represented as phi. So this is your potential function phi, and the definition, what the potential function means, is when you take the gradient of phi, you get the velocity. But you can only do that mathematically if there is zero vorticity. So if there's zero vorticity, the flow is irrotational, and then we can explore the flow using this potential function as a mathematical tool.